Talk to one and then we
skip forward in terms of. Well, thank God.
You're okay?
Yeah,
Okay,
thank
good.
God. I got caught up now. I caught up now.
Sweet, sweet. All right, guys, it's about 4 o'clock. I think I'm gonna go ahead and try to get started here. It's really great to see all of you. I hope that you had a good weekend and that things are going smoothly for you. I know it's a busy time. We're kind of back from spring break, now doing this final push, and I just thought about it. We only have 3 weeks left. You only have to listen to me give 5 more lectures, something like that. Hopefully you haven't been counting it down for too long. Yeah, only three more weeks, so that's 6 class meetings. One of those will be an exam, and then after that we'll have just the final left. So we're getting close. In fact, today we are going to finish talking about chapter 8, which means we will only have 1 chapter to go. But you know which chapter is the best chapter. The thing I love about this class is that the best is always yet to come. The last part is the best part, is where we're putting everything together from the entire semester. So chapter 9 is going to be awesome. Every time I get to go over the chapter 9 material, I've always it really makes me proud of this course and just how it's been set up and laid out. And it should be a lot of fun. I'm looking forward to that. Before we get to that, a couple of other comments. First of all, thanks to all of you for watching my video. I know the quality of the video part was questionable. The lighting was kind of on and off, and I hope you didn't get too blurry-eyed after watching that. I do apologize. I probably just need to re-record the darn thing on my phone because my laptop wasn't that good. But the audio, I think, was okay, and I saw that every single person did it. So that's 100% of you guys actually took the time to watch it. Did it seem okay? Did you follow it all right with the examples and stuff? We're going to practice it some more here right now, but section 8.3, the annihilator method, that was what I wanted you to see in that video, and I appreciate you taking the time to watch that. So we'll practice that a little bit more, and then I'm going to talk about what do we do if the annihilator method doesn't work. Is that even possible that it couldn't work somehow? So that's a question. And I want to practice the stuff that was in that video today as well, to give you guys a chance with some hands-on problems to see how you're doing. There's no homework due tonight. In fact, this week we just have 1 assignment, which is the one I want you to do for Thursday on the annihilator method. So there's just 1 section of problems to do. On Thursday, I will take questions on it. So probably you haven't had a chance to work through all of it yet, but if you get going on that homework and you have some questions, you can also, if you want to get an early start, you can ask me questions tonight in office hours as well. Otherwise, Thursday will be great, and we'll kind of put a closure to that section, and I think we should be good. That's about all I have by way of announcements for now. I guess the only other thing I'll say, about half the class has filled out an SOQ so far. We got to get you guys up to 85%. I want to get a really strong feedback from you guys about the class. Actually, I'd love to get your comments about the videos. If you haven't filled one out yet, are they helpful? Because I didn't used to do videos. So if the videos are helpful, I'd love to know whether I should keep doing that or whether you'd rather just have it all in class or whatever. Stuff like that is just good for me to know. Things that you liked, things that you didn't like. You've got until May 2nd, which is about 10 more days still to fill that out. But I would recommend just go in there, fill it out, get it done with. As we get closer to May 2nd, we're also going to be getting really close to our next exam. And so you're going to have some other things to distract you at that point. So I'd recommend getting a little bit of an early start on that. Right. Okay. So what I'd like to do before I get going on this recap here, I have pulled up our Canvas page, and I'd like to show you something in here briefly. You don't need to take any notes on this first little thing I want to mention. But in the special handouts folder, this actually also something that came out of my SOQs a few years ago. The students had mentioned, the math is great, love the math, everything's fine, but we want to see, like, where does it actually come up in our engineering world that we live in, because 90% of the students that take Math 250D have some kind of flavor of engineering that they're working on. So I just wanted to pull up, there is a handout in here. Again, this won't be anything I'm gonna test you on. It's nothing that you need to worry about too much. But there is it's another one of these things, I just drew it out by hand. Let me see if I can possibly make that any bigger. Scroll this thing up a little bit. So is that legible at all? Go up here. Yeah, so these higher order linear differential equations, they do show up in the real world applications that you probably are seeing in some of your engineering classes or will see. And so there's a reason we're learning all this stuff. A great one is oscillations of a mechanical system. So students mentioned in the past, it'd be nice if I just mentioned these briefly. They are actually covered in our book, but we're skipping those sections because they are really more reserved for your engineering classes than they are for this class. But if you have a spring with a mass attached to it and you give it a little initial velocity and have it bouncing up and down, the motion or the position of that spring as a function of time is something you might like to solve for. And we call this y of t. It's the position at time t. And this mass position satisfies a differential equation for free oscillations. Free oscillations just means there's no external forces continuing to act on this mass once you give it an initial tug, right? It just freely oscillates in the air. And depending on various constants, there's a spring constant K. The mass has a value of M. And then there's a C value, which is some kind of a damping constant, something that sort of tends to make the oscillations slow down. Eventually the mass would come back to rest again after a while. But yeah, here is a differential equation for that, right? It involves the mass, the spring constant, the damping constant, and it's a quadratic, it's a second degree, homogeneous, linear, constant coefficient differential equation. Exactly the equations that we've been looking at in chapter 8. And so as usual, you can solve for the roots of the auxiliary equation. There's going to be a couple of roots. And depending on whether those roots are repeat roots, whether they are complex roots, or whether they are two distinct real roots, we get three cases of how this mass is going to move as a function of time. So I've kind of drawn some graphs of the y of t as a function of t, right? Depending on the situation. So like, for example, if c squared is less than 4 km, that would be the case of complex roots. So you could have like a plus or minus bi. In that case, you have sines and cosines that show up in the behavior of the curve. You can see it here. It looks like sines and cosines that are getting damped down as time goes on. So that would be one possibility, what's called damped oscillations. But then there's other cases as well, depending on critically damped. That would be the case when you get two real roots that are repeated, right? So in that case, you won't have sines and cosines. This thing is going to come to a, I don't know if you've ever pulled a spring where it like stopped almost immediately, but that's essentially what's going on here. This spring doesn't have nearly as interesting of a trajectory. Maybe it's very stiff. It could be a very stiff spring that just doesn't allow for this long-winded oscillation behavior to happen. So you might have a very different behavior in this case. Again, it all depends on what C and K and M are, right? And so there's those three main cases that you can look at. So that's one example. And then on the bottom half of this handout, if I can possibly scroll this thing down. Sorry, I guess I should be able to just do it this way. Another example, for those of you who are more interested in like the electrical engineering applications, we can set up a similar discussion about circuits. So if you have an electrical circuit that has some kind of a battery and a resistor and a capacitor and an inductor. I studied all this too because I was a physics major. I hated this section. But anyway, I still had to put it in my book. It's a very similar thing. You get a second order differential equation that governs this the charge. You're interested in like, what's the charge on the capacitor at any time t? So Q is somewhere I probably wrote it down. Q is the charge, and you've got resistance, capacitance, inductance, and then there's this battery, which is pumping voltage into this circuit as a function of time. This time it's assuming the battery isn't just sitting there with no force on it, there is a non-homogeneous component to this. So this one would be something we would handle with, for example, the annihilator method potentially. And again, there's a quadratic equation for the auxiliary equation. You can solve for the roots, and depending on what kind of roots you have, that's going to greatly impact the behavior of the circuit, the charge on the circuit as a function of time. So anyway, that is another nice application. These are just two applications. There's of course many others, but I just wanted to show that to you because I think in this class it's easy to kind of lose track of like, why are we doing this and who cares and like, what's this for and all that kind of stuff. So there is at least a brief snippet for you of an overview of it. I'm not going to hold you responsible for it. It is in the book. If you want to learn more about it, you can always take a look at it. Come talk to me about it. Just don't tell anybody I don't like that one section. I didn't write that section about the circuits. But anyway, that's it's just my personal thing. You can't touch and feel the charge going through the wire. So I think that's what it is. With the mass, I can watch it and see it and play with it. But anyway, that's a nice application. While I've got this folder up, this is the special handouts folder in Canvas. I should mention that this is also the place where you can find the annihilators and integrals table that I was referencing during the video that you guys watched. So somebody asked me over the weekend about this. I am going to be giving you this handout pretty much for every exam from this point forward. You do not need to memorize these annihilators that I was going over in the video. I'm going to give you do need to make sure you know how to use this information correctly, which is part of what the practice is about. But I will give you this list. Don't try to memorize all this crazy stuff here. And then it also has this table of integrals on it, which we are going to need as well. So I'll just be giving you this basically from this point forward. Anytime that we have a test or anything like that, you'll have that at your fingertips. Okay? Any questions so far? So far, so good. Okay. Well, what I'm going to do next then is we'll kind of keep that up maybe because we're going to practice a little bit more on this topic from the video. The video had some good examples, but I want to do more examples. And by watching that video, it enables me to give you even more examples. So there's a 3-step process that I was talking about in the video for how to solve a non-homogeneous differential equation. And the 3 steps are, first, to solve the corresponding homogeneous differential equation. So you simply forget about what the f of x is and just treat the right-hand side as 0. That would make it homogeneous. And we solve for this thing that in the video I referred to as the complementary function. Okay, but this is actually nothing new. This is the same stuff we learned how to figure out last week. Last week, I think we did a 14th order differential equation. We solved one of those. It was a huge thing. That whole big answer would have been like the complementary function in that case. The more recent issue, though, is that we also have to find, step 2, we have to find one particular solution. And this is going to be denoted the y sub p of x. All right, so we have to find that, and that's what the annihilator method will allow us to do. And then the third step is easy. We just have to write down that the final general solution is the sum of what we've obtained in the first 2 steps, the complementary function and the particular solution. I mentioned in the video that for step 3, you don't need to write out fully. Imagine that I gave you the 14th order differential equation and you did step 1 and you wrote down 14 terms. And now you get to step 3 and you're like, oh, great, I have to write down the final answer. So I've got to start by recopying 14 terms down again. No. I learned this early on to not ask people to do that twice because it takes half your time to just recopy what was in step one. So if you want to just write this down, literally, right? And if you write this down, maybe you don't have, maybe this is wrong, but you write this down, I can give you credit for knowing that part of the process is putting together the complementary function and the particular solution. So again, it's all in the spirit of trying to demonstrate on, for example, I'm thinking like in an exam situation, demonstrating as much of the knowledge of this whole thing as you can. Step 3 is an easy one to demonstrate, even if the first 2 steps maybe didn't quite pan out perfectly. So just keep that in mind. I always like to give people partial credit when I can. Let's do, first of all, are there any questions about this sort of 3-step overview or anything from the video that is related to this so far that may have given you guys any trouble? Yeah, I made that video last semester. I had to miss a class in the fall, so I just decided to make it, and I like everything about it except the video quality. Should have used my phone, but that's all right. I'll try and work on a better one. But let's try to practice this method one more time. Just make sure everybody's good with it. So here we have an example. This could be our electric circuit. It could be our mass on a spring, who knows? But let's try to solve this differential equation. Y double prime minus 3y prime minus 4y equals 15 times e to the 4x. All right, so I like to just go right into the first step. There's 3 steps here. So I'll focus on the step 1. And the step 1 is to just ignore the right-hand side and focus on the homogeneous differential equation on the left side. And as you can remember, the very first thing you need to do, guys, is find the auxiliary equation. This is obtained by turning the d's into r's. Well, it's like, where are the d's? The d's are literally just the derivatives that you see in this equation. So a lot of times I'll rewrite my equation in the d notation, which is what I've now kind of put below the question here. And what I'm going to do is turn those d's straight into r's. So r squared minus 3r minus 4, and this is going to be set equal to 0 here. Okay, so that's my auxiliary equation, and it's a quadratic equation, so I know that I should be able to factor it. If I can't factor it easily, I'll just use the quadratic formula. But this one actually does factor pretty nicely. R minus 4 times r plus 1 is equal to 0 still. Okay, so we're going to get 2 roots here, which are 4 and -1. All righty, and from that I can already write down the complementary function. There's no complex numbers here. There's also no repeats of roots here. So the issues that we kind of talked about last week, the issues that we sometimes have to be careful with, don't arise at this point. So I'm going to go ahead and jump straight to the complementary function directly. And remember, we're using, what is it? E to the Rx as our trial solution. So in this case, that would be C1 e to the 4x plus C2 e to the -x. And let's try and put a box around that so that we can easily find that later if we need to. Okay, so that's the first step. Not too bad, right? Okay, so let's go to step 2 then. Step 2 is where we are going to think about an annihilator for the right-hand side. So 15 e to the 4x. This is what what I had you think about during my video. Remember that the 15 that's in front here does not matter at all. So in my video, I talked about that. When you take derivatives, these constants are always immune to what's going on with derivatives because you can always just factor constants out of derivatives. So the 15 really makes no difference. And so you're thinking about e to the 4x and how to annihilate it. You can either have that one memorized, because it's a pretty easy one, or if you don't have it memorized, just come to the table. Item number 2 in the table, and I know that's probably hard to read from the back of the room, but the annihilator of e to the ax is just D minus A. So in this case, the A value is 4. So the annihilator, I'll write it here, A of D is just D minus 4. Okay, so we just have a pretty easy time of it with that. As I explained in the video, what we technically will want to do now is apply that annihilator to both sides of my original differential equation. The effect of that will be to turn the right-hand side to 0, because you're annihilating it. And then the left-hand side will, in addition to the D operator that's already here, you will now pile on an additional factor right here, which ultimately will lead to an additional root of your auxiliary equation. But for step 2, I really only care about the quote unquote new roots, right? So these roots here, I should have, in my video, I talked about these and referred to them as the old roots of my differential equation. The new roots are just whatever roots you would get from this. Well, again, turning the D's into R's, you see right away that R equals 4 is a new root. So step 2 is always where you would have any new roots. In this case, we have R equals 4. Okay. And keeping in mind that the old roots correspond to the terms of the complementary function, and the new roots always correspond to the terms of the particular solution, we can now write down the form of the particular solution. And what would it be, guys? Anybody want to give me a try? C3 x e to the 4x. Why do you have an x here? Okay, even though it's a new root, even though the R equals 4 is a new root, we have to be aware that it actually was also an old root. So I talked about that in the video. If the new roots are already repeating the old roots, then that counts as repeats. And the repeated roots situation is what we talked about last week, is where we have to stack those x's. Remember that? So we would stack x's on the front of this expression. So I have e to the 4x times x. And then there would be a constant here as well. Now I am going to change this constant. You might remember in my video, I don't like to treat this constant here on the same footing as the constants of the complementary function, because this constant actually has a specific value that we can find. Let me just refer to it as capital A for now. Okay, so other than that, I mean, it's not wrong to call it C3, but it would just be easier to keep everything straight if we just use like a different notation here. Okay, and the A is to be determined, and that will actually be somehow related to this 15. So far, the 15 has not come into this problem at all, and of course, it should make a difference at some point. So what we have to do now, guys, if you remember, is take this particular solution and plug it in to the left side of my differential equation and match it up to the right side. And hopefully the dust will settle in such a way that we can find the value of A. We actually should be able to find A here. Now, if I leave it the way it is, what we would do is we would call this the form of the particular solution. And I talked in my video about it. I just want to remind you again. Sometimes I will only ask you to find the form. In other words, I'll let you just stop here and call this good for step 2. So sometimes I will do that because, why would I do that? Well, it's because at this point I have to take a whole bunch of derivatives of this thing, and it could be horrendous, and by hand it might take forever and not be a good use of time. So I might only ask you for the form of the particular solution. You guys will need to read the questions carefully when we get to an exam on this. If I don't say anything, if I just say, find the general solution, then you got to do it. You got to find out what A is. You got to keep going all the way through it. But read carefully, because I might say something like, it is okay to just give me the form. The other thing is, if I do make you solve for the constants, which I'm likely to do at least once, maybe twice, just to make sure you can do it, it's not going to be worth that many points in terms of the big picture of the exam or even this question. It's just one piece of it. So try not to get, I've seen this, I'm saying this because I've taught the class so many times, I've seen it happen where somebody will spend 30 minutes during their exam getting screwed up on solving for this one number. And what they don't realize is that, that might be worth a couple of points, something like that. It's just not worth it. So I'm not trying to downplay this as if like you shouldn't care about how to do it, but just be smart about your time management on an exam. I mean, even right now, taking one derivative of this, I'm gonna have to use the product rule. So it's gonna take a little bit, but I'm gonna do it, just so I can't ask you to do it if I don't do it. So I should at least do a couple examples of this to make sure that we're good. So the first thing I like to do is just calculate all the derivatives. And I see that I need up to 2 derivatives here. It's a second order equation. So I'm gonna leave the A totally factored out. It's a constant. And I'm gonna do the product rule inside these brackets that I'm drawing. So I would have the derivative of the first term times the second term, that would be e to the 4x. And then plus the first term times the derivative of the second term, which would be 4x e to the 4x. Okay, so that's just the product rule so far on that. If you wanted to, maybe we'll do it. It doesn't really have to be done. I can factor out the e to the 4x here, and it'll leave me with the quantity of 1 plus 4x. And we need to go one more derivative on this. So let's go ahead and calculate yet another derivative. So again, the A can be pulled totally out in front. And then I'm going to use the product rule again. So I'd have the first term times the derivative of the second. That would be 4 e to the 4x. Plus the second term times the derivative of the first, which would be 4 e to the, derivative of the first times the second, 4 e to the 4x times 1 plus 4x. So again, I have another product rule here that has to be dealt with. And again, I might recommend that we can factor out the e to the 4x since it occurs in every single term here. So let's just clean this up a little bit. I'll pull out the e to the 4x. After I do that, I actually have 4 plus 4 plus 16x. That would be 8 plus 16x in total. If I'm doing the math right, anybody can correct me if I seem to be doing anything wrong, but I think that's okay so far. Let's come back over here. Questions so far? Looking okay? Does this look like I'm
saying you could have brought the 4 outside, like, on the bracket. On the second.
Oh, here?
Yeah.
Oh, I could have. I definitely could have. Yeah, I could have. Let's just try to plug everything in now. So I'm gonna plug in to my left-hand side. So, I have the y double prime minus 3y prime minus 4y. And remember, all of that is, let's just come over here, give a little space, but the right-hand side is supposed to come out to be 15 times e to the 4x. So now I'm just gonna substitute in what I have so far. So I have the second derivative of my particular solution, that would be a e to the 4x times 8 plus 16x. And then I have minus 3 times the first derivative, so that's minus 3a e to the 4x times 1 plus 4x. And then we have minus 4 times y itself, the original y itself, which was a times x, ax e to the 4x, right? And all of that still equal 15 e to the 4x. Okay. So you see how a lot of this is just tedious. It's not like this is like heavy conceptual brain power. It's mostly just not getting lost in all the calculation here. Now, every single term has e to the 4x in it on both sides of the equal sign. So to clean this up the best, I think it would be best off to just cancel the e to the 4x's everywhere that we have them in there. And then we have a 15 on the right side. Now, on the left side of what's left, let me just point something out here. Some of the terms on the left side have an x in them, and some do not. But we actually already know that there's no x's on the right side at all. So the x stuff on the left side that better cancel out. How many x's do I have on the left side? I have 16x minus 3 times 4, that's 12x, and minus another 4x. They do cancel out. Right? So you can think of it that way. It's like, you know, this is something plus something times x. I know that, but the something times x part is there's 16a minus 12a minus 4a. This just cancels to 0 and doesn't really help you. You're not going to be able to solve for a based on that. It's the constant term that is the key here. The constant term has an 8a here in front, and then minus 3a right here. And then there's no constant term here because there's an x in front of that. So this is it. 8a minus 3a. So that gives me 5a equals 15. And so a is 3. So a is equal to 3. And all that work to come up with one number. That's the way it goes. And so the conclusion is that we can now fully express our particular solution, which is 3x e to the 4x. And this would be good for a box as well, because we want to be able to easily find that. That's the particular solution. So all I did is I took the form of the particular solution and I put in the a value, which I had just worked out as being 3. Does that look okay? Any questions here so far? The last thing we have to do, step 3, is to just write down the final answer. So let me put that, I'll squeeze that in right up here at the top because I got just enough room. I don't need a lot of room for this. The final answer is just, you can kind of go on autopilot here and just kind of write it down. Y of x equals y sub c of x plus y sub p of x. You can leave it at that if you don't want to recopy everything out. Now this one is small enough. I sometimes, when I can, I kind of like to see what it looks like. So I'm going to do it just so you have it for your notes. C1 e to the 4x plus C2 e to the negative x plus 3x e to the 4x. This would be the answer. Right there in that box. One situation where you might really want to write it all the way back out again is if there was an initial condition provided. Now, in the video, I didn't have any of those, and this one's not like that either. But if there were some initial values, like what y of 0 is, or what y prime of 0 is, I might ask you to solve for these constants. And it's very important that you do not solve for any constants that might show up until step 3 is done. So you can't solve for C. Some people have tried this before, tried this little trick, it's not ended well, is that if you try to solve for the constants by using the initial conditions right here at step 1, you will not get it right because you're not incorporating the particular solution into that, which is part of the solution. So it's important to wait until the end to solve for the constants by using initial conditions. But that's what you would have to be given in order to solve for those constants. And as I said, other than that scenario, you really don't need to recopy this whole thing out again, especially if it's a 14th order differential equation. This one's not so bad. As you can see, it doesn't take that much to just write it down. Okay, questions? People feel okay about this? This is the annihilator method. Not too bad. Okay, I tell you what, I'd like to let you guys practice a little bit. I've got some examples here, just a couple of them. And I'd like to let you grab your 2 to 3 to 4 partners, whoever you want to work with. And there should be plenty of room to get a lot of you up here. Now, I am going to pull that table of annihilators down. So if you need to refer to that, you might have to get on your phone or something. I forgot to bring copies of that to hand out as well. But I would like to give you guys a chance to practice with your partners. Are down to do this, okay? Just a few more back to this part of the room. And Once you have a handout, guys, you are welcome to go ahead and come on down. I will let you work at the boards.
So once we get there, we'll apply.
Thank you. All right. You guys gonna be a five something?
Yeah.
Okay, sounds good. Hey, Alex? Joe, do you have a partner? Okay, oh, you guys are a group. Do you wanna come see all this part of the board up here? That'd be great. Let me see the bushes.
I didn't hear you, sorry.
Around a little bit. You guys aren't gonna make any mistakes, right? So this can go all over YouTube and it'll be fine. 5,000 people can look at all your stuff.
my face and you should be fine. Turn on
Yeah, blur out the faces, yeah. No pressure, yeah, right.
Back out the arm.
It's fine.
Back out the arm.
Let me take the hard part.
Back out the arm. Arm time. Arm square. 6 arm plus 20 arm.
So one of them is your.
I actually have the table of
Ours
annihilation
are-
side,
What about?
on the side
This thing?
So.
No,
No,
you can't.
Oh, well, I don't wanna do this.
So you need to do the quadratic formula
Plus
and
6
ours.
plus minus 36 minus 100.
Where'd you get 16 from?
Yeah,
Yeah, it should just be 6. Negative.
Oh, no,
plus.
it's-
That's plus.
My bad, yeah, it's positive.
This guy did positive 6 plus or minus, bro.
Right.
I was saying, so it's negative.
36 minus.
You know,
Yeah. Keep going, bro.
Yeah, you're on camera, just keep going.
No pressure.
No pressure. No, bro, don't put me in.
He's
Put
next.
him like right here.
He's next.
I don't know.
Wait, hold on. Let me adjust it.
Yeah.
Oh, let me know. Is that good?
Right, yeah, perfect.
That camera.
Yeah,
There you go.
Now you get to do it, bro. Now you get to do it.
Yo, put it at like right here, at Sufyan.
So, come on, man, let's do the math.
Yeah.
Is it
So-
64?
36 minus 100.
60.
64,
which
is
8,
which is.
Well, square root of 64 is 8.
Yes.
Then you're done. But it's negative, right? So it'd be 8i,
Oh,
8i. Yeah.
Oh, yeah, it's negative.
So 3
plus- Cosine
so
sine.
3
plus or minus
4i plus minus 4i.
That is correct. 3 plus or minus 4i.
And then.
And you have another root besides that too.
Root of 0.
So ours would be 0,
Good.
3 plus 4i, 3 minus 4.
And even your hand gets tired, just kind of work it along. So good.
Wait, Andy. I'm at a 47% there.
No, bro, you're like right there though.
You see the circuits? or
It's. Dude, that's not even that bad, bro.
Friends look like 56, 70. Isn't it a D plus? Isn't it a D plus?
Yeah, no, what that is, that does matter.
You got nothing to worry about, bro. You good. Are you happy now after seeing this? You chill, right? Now
You got 100% and 94%.
What?
RTOS?
Oh, that's because he doesn't put in bullet anything.
Oh, yeah, bro.
Yeah, it's very cute. I'm here at the end where he goes 100%, I'm like 30. I'm like, that's like the one class where I'm like,
Nah, he doesn't fail people. Terry doesn't fail people.
thank God.
Yeah, he's low key to go at like not failing people. His lectures might. His lectures might not be the best.
No, it's not.
Body.
General.
Is it like a lot?
That's for the for the next section. Now if you go for that.
Yeah, that's good.
Perfect, perfect.
No, this is not Professor being an idiot. What she do, she pull on every single homework assignment, and then also every single like assignment and put zeros for all of
We
them.
gotta ask there.
Yeah, a lot of professors.
D.
So I have no idea what I have in my class right now.
So next week, D is a K plus one.
Let me bring.
I'm bad at it.
Okay, so D.
Yes, after- Why don't you pass that marker to your next, whoever you want to pick on.
This guy, bro.
I know.
You did a great job on step one. Let's let someone else write up the step two.
Guy, bro.
Yeah, give everybody.
I wanna take my revenge right there. What you did to me. Better try to bro.
Hey, we got put on the spot last week too. So I think it's D to three.
Let you finish that. Like, so far, so good.
K plus one. That's next.
K plus one. It's kind of like saying.
That's what, yeah. It's the. That's that.
Yeah.
I would call.
So I think it's D. On this side, in this case, now you can turn it into R. And then now let me.
Recording is.
Because he just said that.
Right.
Yeah, so, yeah,
Oh,
once we
yeah.
plug in the we just have to wipe the others.
I mean, I guess I did.
It's the annihilator functions, right? That one.
If you set that to zero.
That's fine.
This is our new. Yeah, that's your new root. So set it to zero. So R is equal to zero, so it's gonna be
You
muted,
guys have 100% on this.
right? Because we have a zero on the first one. So we're gonna add an X to your thing. So this will be C. So we're gonna find T and C. Man, my brain is cooking today.
We would switch the C14.
Yes.
You are in the way.
What?
You are in the way.
Bro, what I cannot see it, that's why like. What is it? X. I don't think
Doing okay here?
Or no.
My old-
No, it is zero. Is there any older ones? Or just one? So.
Actually, I don't.
Go for it. I don't wanna get.
Right there, the I, 3 plus. Oh, yeah, sorry.
Now we can try to.
And then these are.
No one needed to.
Even though our zero.
Because that's.
Oh, yeah, okay.
Yeah.
Wait, hold on, because zero repeats, right? So that's gonna start.
So.
It's stacked there. Yes.
Repeat is what I said. But isn't that RQ shouldn't be repeated 3 times?
Wait, yeah, she might be.
I actually did it. Cause
It's RQ.
Here's the irony.
Yeah.
That'll be the fourth one.
Yeah.
We can submit it like 3 times.
So zero stacks all times.
Yeah.
It's the fourth.
It just like so it just like
So,
2
like-
times, yeah.
But. No, we just X.
Power.
X squared then X.
It would be B.
Like a different, yeah.
Yeah.
Different constant.
Plus BX plus C.
Because it's very.
Right.
No,
Yeah,
no, you have to stack the X again, so it's AX plus BX squared plus CX cubed, yeah.
Yes.
Yeah.
Yes, that right.
Wait, but what did the A be by itself first? Or did it be A plus BX plus CX squared plus DX cubed? What did the A's?
Because he had like.
Yeah, you know what? My comment there, Andy, is when you wrote R equals 0, I would write 0, 0, 0. I would actually write it 3 times. Because, I mean, I know what you mean, and as long as you're clear with it,
We
it's
caught
fine.
that like going for it.
Yeah, just to be totally solid on it, I would do that. But hey, that actually is great. AX plus BX squared plus CX cubed looks fine. What is this thing on the left?
Oh, it was in C4, but then we switched it to like an A.
Oh, okay, yeah.
Like the.
Correct, yeah. So you are good to go in terms of, that is the form of the particular solution.
So we can just plug in.
And we just do the X equals Y.
Yes, except that, what do the instructions say on problem 1? determine the form of the particular solution. So they're not actually asking you to solve for A, B, and C here. You can circle that and call it good, right? The reason is, I mean, I actually did it in the solutions and you get these double and triple digit fractions for the constant. So it's a little messier than you might hope for. So I decided, let's not torture people too much with that. So that looks great. And so then you just have step 3 to write down. And once you get that done, then Andy, feel free to call on another player to take over for you. Yeah. Yeah, and that's why that is true. So this is actually the second, third, and fourth time you leave that route. And the reason that that's reflected correctly in your test side is that you stacked an X already on the A. Right? If that root 0 had not shown up originally.
I assumed it's too much.
That's what I was thinking,
Yeah, that's right. So you're just continue stacking wherever you left off in step 1, the stacking continues in step 2. All right, good job. Anybody need a hand?
Wait, where were you?
That is beautiful.
No, for the AX.
Oh, so we could use the A solution, the easy, or what was
Maybe
it?
we're just asking them for like. First,
Yeah,
that's why
Yeah,
we're first.
R was 3, 3,
Go with just A, BX, particulars.
That would
No,
be great.
negative 3.
That would be great.
If they were next to each other, the first one didn't have like right there, or I should have been like A. That's, yeah. It's because of the all that it's like.
That's like EX.
Which turned into negative.
That's what
Okay, right in front of you, it has not had a turn for the worst.
So just do R plus 3 and then R plus 3 again equals 0, and then R is equal to negative 3 twice.
You guys get that vertical before?
Yeah. Roots.
We used to.
I know when it does the steps, like I have to follow that too.
Not
Now
right. That's like what other question would say.
you do the C1.
C1.
the C is negative 3x, and then I think it's stacks.
Right. Bro, you're chill. I mean, you're like right there. Dude, like I gotta hope
This
for
is last one, right? For like
That's
last-
C2.
Yeah,
literally and extra credit, getting everything.
Yeah, C2x to E to the negative 3. Cool, that's the first step.
Right?
Have you turned in the box?
Yeah.
Put yourself in a
Yeah, but okay, so wait, I know. It's not doable, bro. I honestly. That I thought I did better than what you can put it later. No, I did. Yeah, the 5.1, and then you see it.
To the negative 3.
Like,
E to the negative 3x.
Oh, no?
Negative.
Yeah, there's
There's no like depends on like what it's given though. So if it's negative 3, then it would be like that's negative 3.
So it has to be D plus 3.
D minus A is negative 3, so D minus.
So we D minus
C
minus.
D plus 3.
Yeah, so that's.
Because it's a minus 3, right? So you do.
Another freaking negative 3.
The
So if we repeat.
annihilator is D minus 3 or D minus 8, but then since it's a negative 3.
Oh, so,
Minus.
X squared E to the negative.
Yeah.
Oh yeah, instead of like 6 feet, we could do
I think it's X squared because it's yeah, another repeat.
I think we go for A first.
Into an A form, and then now we have to solve.
Nine.
The original equation has two derivatives, next so we have to pick two derivatives. Negative 3. 3. Just toss. Be like this.
Once we have to start doing like power rules and stuff, yeah, I'm like, nah. Yeah, dude, I know. I'm gonna be like, wait, like I haven't done this for a while.
I
Like,
know.
once I get to that stuff, I'm gonna be like, yo, you got this, right, Professor? And then I'm
Yeah,
just gonna go to the bottom. Step 3, y of x, y cube x, y cube x.
I'm just trusting you.
Like put it in parentheses, insert derivative here, and then just put the step.
Do the permute sign.
Oh, yeah.
Checking, so what is the, where is the form of the Lysa?
Should be down here.
There it is, yeah, that is all correct so far here, and now you're gonna start taking derivatives.
Derivatives, yeah.
Okay, you got the first derivative by the product rule, right? And then,
Oh, but there's a.
yeah, I think what's throwing me off, this is plus a negative, so that's actually just a minus, yeah. Okay. So that's like that, and now you're gonna do another derivative.
Yeah, it's kind of like
Gosh, yeah, it's gonna be kind of messy. So, no, it's okay, can I show you something? I take the first term times the derivative of the second, plus the second term times the derivative of the first.
To get the same thing.
So that's what we have, right?
Yeah.
And here's the thing. Okay, so can I take over for a second?
Yeah.
So this looks horrendous.
Yes.
It looks really messy to plug it in.
Yeah.
Because that's the next step now, is to plug it in on the left side. I have to do y double prime plus 6y prime plus 9y. I have to work all that out.
Yeah.
But I'm going to be setting that equal to 4e to the negative 3x. What you notice on the right hand side,
You can take out all the negative 3, e to the negative 3x.
I can do that, but
Yeah.
I'm gonna do even more than that. So I can pull out cancel out all of the e to the negative 3x's, but the other thing is, on the right hand side, I don't have any x squareds. And I don't have any x's. This is literally just, this coefficient is all that's going to be left when I
Yeah.
cancel the e to the negative 3x's. So like when I'm looking at plugging this in, when I'm plugging that in, I can ask myself, anything that has an x or an x squared in it must be canceling out on the left side, because it doesn't show up on the right side. So on the right hand side, I only have a 4. So on the left side, this is gonna cancel. This is gonna cancel. I have 2 and negative 3 here, right? 2 and negative 3, that's negative 6a.
Yeah.
So far, okay? And then what's the next term? Plus 6 times y prime. Where's y prime? Y prime is here.
Yeah.
Okay, again, anything that has an x or an x squared in it has to completely cancel, and that's actually the whole thing.
Just take.
Get rid of it.
So just
So there's
a.
nothing,
Okay.
right?
Okay.
Nothing there, just cancel it. And then plus 9 times, where's the original? This one. Oh, well, that has an x squared in it as well. So that must be canceling partially with some of these other things as well. So that's fine.
Alright.
Except that this is not correct, because the answer for A is supposed to be not negative 4%. So let's see, what's the matter here? Y double prime. This is the first derivative, so. Oh, is this minus, oh, you pulled out an x.
Yeah.
That looks okay, so then we use the product rule, the first term times the derivative of the second, plus the second term times the derivative of this. Well, that was. Did I do this?
Yes, you did.
Am I on camera?
Yes.
Yeah, I need to use the product rule for that, don't I, right? Because this has an x in it and an e to the negative 3x, so there's an a there, and then I have to do the product rule, which means x times the derivative of e to the negative 3x plus the derivative of the first term times the second term e to the negative 3x. Okay, now this part has an x in it, so I don't care about that. But I have an a here. Right, and this is on the y double prime, right? So let's just see. So I'm on the y double prime, I have, oh, and there's a 2a. I'm just looking at the parts that don't have x's or x squares. I have 2a there. Everything else has 2 times a times e to the negative 3x. Everything else that I would like FOIL out on that term would have an x or an x squared, which must cancel with something from here or something from here.
Right.
Okay, plus 6 times, we already did the y prime, there was nothing there, right? And then, so there was nothing here. And then on this one, the y, where is the y? Here, right here. There is no constant term there, the x squared, so that all goes zero. Now we've got it right. A is supposed to equal 2. Sweet. So it's my fault. I did not do the product rule on that, the last part, so I'll go back to school one of these days. Figure that out. All right. So you've got your A value and now you should be able to. Okay, sounds good. Everything is.
Oh, yeah.
Yeah,
I don't even remember it.
yeah, I have to go back to them like.
2. It has a A plus 6 on it.
Yeah.
Well,
So I just took that F on that. That's all.
here's
Yeah.
a 2A
Unless you're passing your.
like
That's what
that.
it matters.
And.
Initial position.
Yeah, but now you're talking about count one again, bro.
I'd rather do calculus.
It's not that hard.
At the.
Depends, like it gets complicated, like one after another.
Yeah, like once it gets to this like.
And recorded.
Oh.
Millions of viewers.
On camera. 1080p, whatever this thing is. Yeah.
Ah.
Can we apply this to series?
Bro, we made a mech, but that's like a super version.
It's game 6 though, but you can go. Yeah, we're the only group with 60 votes.
To be fair though, he did like, honestly, if he could do this part, we'd probably be still stuck on that part.
Oh, for sure. I forgot to mention that. We just get rid of
This
it.
I'm gonna use that on the test.
I don't figure it out.
Yeah, I'm not.
One of the
So
LCs.
I shouldn't have
We
been
cancel out the e to the negative 3x. We
all
got
of
that.
this.
How did you got rid of like?
The other times I had.
We got rid of all the x's, because on the right hand side, there's no x's. So if you go to the x plus
Basically like, yo,
Outside.
So it's a little trick.
so everything has like,
They're
where it has
like-
the x, so it's
On the left side.
So if it has, it will just cross it out.
Take it as 0.
Because the right side is 4 to the negative 3x, so it's a constant, there's no x there. So you said anything that has an x would just get like,
Just over x squared.
Yeah. Yeah, so that whole.
Hey, guys,
Removed.
If you are done or close to done, feel free to take a 10-minute break. This would be a good time to do that, and then we're gonna start up again in about 10 more minutes. Otherwise, if people still have questions, I can still read them out.
Two.
It's underlined.
Good.
This is hard from. This cancels out. This cancels out. This is confusing.
I think what you do is you do your derivative first, and then you see on your right hand side, and then you start.
Some water, so I need some water.
Let's see what you're left.
But here's what I want. On the right hand side. So first of all.
It'll probably be like part B, like, oh, after we that, solve the addition.
And now.
Yeah.
That's fine.
We have a midterm 7 days before the final.
This guy, oh, he's gone. Stop, it was the Tuesday, we have the meeting, and Thursday we have the final. Like, bro, you're
Good shit.
You have no time to study. I check it. This guy's playing.
If the finals on Tuesday, it's all gonna be
No, the final is 15 pages long.
No, but like the simplicity is difficult.
Bro, all I know is he's gonna give us some sort of guy.
It's gonna get stuck on the first chapter.
I actually expect like 30 minutes to a
We wouldn't just have 4 on the right.
And 80% done with the semester. I'm still not that confident with EROs.
2.
Oh, yeah.
100%.
Yo, count to damn near killing me.
All of this stuff over Taylor and how we're.
Oh, don't get talk about this shit, bro. I don't even want to hear that.
Distant washers, make sure you got that bottle washer on scale.
No, I actually did fine on distant washers. Yeah, it's just the other stuff I can't. That's
This all end up making sense here, guys?
yeah.
Okay, we got it all correct for the video now?
Yes.
Okay.
Except the part that I screwed up.
Yeah.
Edit it out, it's fine.
I've got to have to
Edit,
edit that out. That's so embarrassing. The students were doing fine, the professor shows up.
Yeah.
Distant washers, since I can visualize it in my head, I can do it.
It's so gross.
I still the name that forgot.
Right?
No, you have to relate it to.
You had like 3 though.
We don't necessarily have to.
Probably in high school, I did swan home. And combination of everything.
If you don't mind, that'd be really helpful, thank you.
Yes. This direction.
So you're taking 2? Yeah. Yeah, more less hours because I'm doing classes. That's what it's like. Weekends or something.
So, but I couldn't even get some assignment tonight. That's Saturday. Just couldn't get to it.
What's the other level? Oh, okay.
More business.
Yeah, yeah, my finance class, which I can like so well. Oh, wow.
I already won a test after God looking at the roommates of intentional list.
You know,
So.
So I've been feeling like.
So you have to memorize all.
He's gonna let us have it on the test, but you do have to.
So they put out the lab section, but now they're saying.
Yeah, last time I was there.
We like zeros.
Yeah, we like 0 too.
Zero vector check when it doesn't pass that, I'm
Oh,
like.
yeah.
No more work on that.
But if you, we just like when
How to have you
test
have
passes.
this? Yes, yeah. You can always look at the value when it's on the question. If it's like one question worth 10. the whole thing. So it's like, it probably doesn't pass the zero vector. Show 2 sentences.
Then you're like, oh, yeah.
It's expensive. I still haven't looked at this centimeter.
Oh, no.
Like, what my grade is.
Oh,
I know, but I'm like kind of just going.
Yeah, you
I want to
have to,
get down, so.
yeah,
if I look
yeah.
at something. Physics, that's nice.
So this class coming up should be, right?
I think it's more complicated.
Right?
Yeah.
Should be on-
These will be like. It's a linear group of.
You know, and then it comes from there. I'm gonna have to- For How should we?
Thinking 17, but-
See if I can show you. I got here. 60 minutes next semester. No, read. Full dinosaurs.
Covers the pressure in between.
But it's mathematically, it's mathematically impossible. Just do that, I was like, what are these? Just look at it, just can't do that.
I should take it like that. You're like, I'm at. Trying to concentrate. Anyway.
What's that? No, it's, oh, it's gonna be, nice.
Yeah.
They were that.
Sweaty.
It's going on.
My Vietnamese, but she had little to no hair. Took her to like 2 or 3.
Yeah.
And then she hung up a bed. Next kid is 6 months. So it- it's, yeah, it's good. Yes. But she was like crazy. There's more hair. It's more.
Yeah. My son was.
Yeah.
I tried. Very, she was like 5 years.
Yeah.
It's like I have something thrown away. Yeah. But no, it used to go.
Like this. That's what we're.
Yeah.
We're trying to see.
Yeah.
As well as you said.
Yeah.
Yeah.
She'll get used to it.
Yeah.
It's worth a try.
Yeah.
Oh, what are you guys?
My daughter was.
Oh,
Yeah, it's small. No, because he goes there when he's kids.
Yeah. Yeah, that's.
But.
Yeah, well, it just upset me.
Uh-huh.
If I don't get
It's like
upset.
midnight today.
Yeah.
There's no party. Yeah. Yeah, I was gonna say. Yeah.
I see your head just stick up. I got a series. Yeah. Yeah. with YouTube. You can hear it.
All right, guys, I think I might go ahead and try to get everyone's attention here again. I love that so many of you are connected to each other. I know you take a lot of common classes, but you know, this is the best way to get through a lot of classes, not just mine, but a lot of classes, is to sort of have some people to lean on and to work with. And I've been really encouraged by all of the group work collaborations and everything like that. So thank you for that. Thank you for your hard work. And just to remind you, the solutions to the group work that we just worked out are on Canvas. So you might feel great about it right now, but in a week or two, if you're going back and what was I doing on that problem? You can look up the answers again, review it again anytime as we go forward for the rest of the semester. So anyway, but I think most of you got done with that problem, and I hope everybody's feeling okay with this annihilator method. Does it seem reasonable for now? You may hear some other professor call it by the name of the method of undetermined coefficients. Those constants that you ultimately solve for in the form of the particular solution, like the capital A, capital B, what have you. Those are the undetermined coefficients. And so the method of undetermined coefficients, which I'm referring to just as the annihilator method, they're really the same thing. It's just an alternative name that you'll sometimes hear people say. So once you go out of this class and you're talking to other people about it, if they start using that terminology, you'll know what we mean. They're talking about the same stuff that we just learned here. So I thought I would throw another problem at you, and let's take a look at it and see how far we can get with this new problem right here. So I'd like to, again, solve a differential equation. This is a second order differential equation, and you can see y double prime minus 12y prime plus 36y equals e to the 6x divided by 1 plus x squared. Okay, so I'm just gonna jump into it, and we have the 3-step process that we've been practicing a little bit already. So let's just go right into it here for the solution. I'm gonna do step 1. And immediately, the first thing we want to do with that is to get the auxiliary equation written down. And I'm going to do this fairly quickly because this is a pretty easy one to just eyeball it. But when I turn those derivatives into powers of r, you can probably see already that the auxiliary equation would be r squared minus 12r plus 36, setting that equal to 0. Okay. And sure enough, this factors very easily. It's just the quantity squared of r minus 6. So it's r minus 6 quantity squared. And link everything up here again. So the roots this time are 6 and 6. So it's always good to write down the repeats multiple times. And so my complementary function, we should be able to write it down immediately. Does anybody want to help me with it? C1 times e to the 6x. Okay, perfect. And then plus, what's the second term? C2x e to the 6x. So we stack an x because of the repeated root, r equals 6. It shows up twice. So there's the complementary function, and that looks great. No problem so far. So now we come to step 2. Step 2 is where we have to find an annihilator for the right-hand side. Or that's what we want to think about. Remember that when you're using annihilators, what you're really doing is you're using derivatives to get this function to get canceled out. Right? That was in my video, that was the whole big thing I was talking about, is we want to find some combination of derivatives to cancel this out. Now the thing is, if you take the derivative of this right-hand side, it's a quotient, and so the derivative would require the quotient rule, which, if you even remember it, is pretty messy. Low D high minus high D low all over low squared. It's not so nice. And so I am struggling to think of how I'm going to annihilate this right-hand side by taking derivatives. Okay, no problem. We can go ahead and look at our table. Except the table is partially hidden here. The question is there anything in the table that might rescue us? Let me try to pull that up here a little bit more. It's probably a little hard to see that, but what you're gonna notice about this table, and I don't mind kind of blowing this up to show you for a second. What you're gonna notice here, guys, in this table is that the only kind of things that we have annihilators for, look at these 9 items here. The only kind of things that we have annihilators for are powers of x, e to the ax, sines and cosines, and combinations thereof. I don't see anything in that table that deals with fractions, right? I don't see anything that would help me to deal with fractions. Now, every semester I teach this class, somebody comes along and makes my hair go a little bit grayer on the exam. So what I'm about to say is what I don't want, don't let it be you. Somebody's gonna do it, it's somebody who's not here today. But somebody will come along and say, oh, I know how to annihilate this. Don't write this down. Actually, let's put it in red. Because it'll get the red pen faster than anything else in the world. I'm gonna do d minus 6, because that'll annihilate e to the 6x. And then on the bottom, I can annihilate 1 with d, and I can annihilate x squared with d cubed. So they're finding the annihilators of each little piece separately, and then just kind of making a corresponding fraction out of it. First of all, this does not make any sense at all. I don't even know what this would mean to be dividing by d. And it's just not correct. Like, I wouldn't know what to do with this. So please, guys, don't go there. Okay, that actually doesn't work at all. Okay, the problem is this function on the right-hand side does not have an annihilator. It just doesn't have one. It's not in the table. We've just thought about it for a moment that we would have to have some crazy quotient rule expression to even take derivatives of this anyway. There is no good annihilator for the right-hand side. So if we start thinking about step 2, which is where we're supposed to annihilate the right-hand side, there is no known annihilator for that function, capital F of x, which, as we said, it's e to the 6x divided by 1 plus x squared, right? There is no annihilator for it. And this is the one and only real downfall of the annihilator method. So if you like the annihilator method, you're not alone. A lot of us do. I love it. It works great. But the situation where the annihilator method is going to fail us is if we don't know how to annihilate the right-hand side. So we need another idea. We need another way of handling step 2. Step 1 is fine. Step 3 will be fine, but we need a new approach to step 2. And it is something that I'm going to refer to as variation of parameters. This is another alternative that we can use if we don't know how to annihilate the function on the right-hand side. And so this is the title of this little lecture here, section 8.7. So you notice I've skipped the section on the mechanical system and the electric circuit and all that stuff to jump ahead to the mathy part, which is in section 8.7 here. So I'm going to explain this variation of parameters method. So we need another approach, and it goes by the name, which is what this section is called, variation of parameters. Now I'm going to put a little asterisk next to this title of this. I'm calling it variation of parameters, but I'm going to put a little asterisk here, guys, because it turns out that, so now I'm going to give you one of the bad things about the variation of parameters method before I even teach it to you, which is that it becomes a mess if the differential equation is a higher order, is much higher order. So we are only going to do this method. We only do this by hand for n equals 2. So in other words, for a second order differential equation. I'm only gonna expect you to be able to do this for a second order differential equation, like the one that's on the board right now. If the differential equation is third order or fourth order or fifth order, there is a variation of parameters method that will work for that, and it's even discussed in the book. But it's a mess. It's a mess. And as I described how the n equals 2 version works, you're gonna see and probably believe pretty quickly that you wouldn't want to do any higher order differential equation than n equals 2 by this method by hand. So you can take it as my oath to you that I will not be asking you to do this method for anything of order more than 2. So that 14th order differential equation we did the other day, that better be something we know how to do the annihilator method on, because the annihilator method will work really for any order. It's not too bad. But for this method, as you're going to see, it's difficult to do it for equations of higher order. Is that a hand?
Yeah.
Edgar, yeah.
So like on an exam, will you tell us outright the process that you want us to do, or will we have them deduce that just based on the right side of the equation?
I don't like telling people which method to use, because I think that's part of the learning, is to know which tool to pull out of the box at which time. So I'm very likely to not say anything. I'm very likely to say, here's the differential equation, now solve it. And I'll expect you to know whether you know the annihilator of the right-hand side or not, or whether the order of the differential equation is too high for you to use this new method, right? So that is something you're gonna, of course, be practicing here as we go through this. Okay, so anyway, just wanted to start with that little caveat. We're only doing this for n equals 2, but if we're willing to do this, this is a new method for step 2. So let me explain how this works. We will guess another one of these trial solutions. And how do we do this? Well, the first thing is, I'm going to come back to the complementary function again for a minute. The complementary function, as you know, we would be writing that if it's a second order differential equation, there will be 2 terms. If it's second order, then your auxiliary equation is quadratic, means there's 2 roots, means you get 2 terms, right? So I can write those terms as C1 times y1 of x plus C2 times y2 of x. So this is the complementary function. And then what is the trial solution? I'm going to slip this down here below. It is y sub p of x. So this is this whole thing again, I told you last week, I don't really care for it so much, which is where you have to sort of guess a solution. Somebody way before me and way smarter than me figured out a good way to guess the particular solution. And that is to vary the parameters that we already see in the complementary function. The parameters up here are C1 and C2. And I'm going to vary those, and I'm going to change C1 to U1 of x. So I'm going to write it as U1 of x times Y1 of x plus U2 of x times Y2 of x. This needs to be in a box. That's something you absolutely have to know. So the form of the particular solution in this case will be U1 of x times Y1 of x plus U2 of x times Y2 of x, where U1 and U2 are to be determined. Okay. So we have to figure out what are these new expressions U1 and U2 that we are seeing here. But the point is that the C1 and the C2, those are like constant parameters, and we are going to allow them to vary now as functions of x. They're not constants anymore. they're going to depend on X. So somebody figured this out, that if we try this form of a particular solution and we go back and we plug it into our original second order differential equation, that we can solve for U1 and U2. It turns out that there are formulas for the U1 and the U2. So there's a couple of things here, guys, in this section that we need to memorize. This is not a hard section because it's very short. It's just dealing with this one little pinpointed step 2 issue. And you just need to know a couple of things. You need to know what is the correct form for your particular solution and what are U1 and U2. So we can derive what U1 and U2 are. We can derive, and I think I'm going to come back over here and do that. I'm going to erase for the moment this complementary function. I want to keep that screen up for a minute because we're going to need to come back to that in a second. I'm going to give you the formula right now for what U1 is, U1 of X, and what U2 of X is. And then I'll derive it in a minute, okay? So the formula for U1, oh, there's a dreaded thing right there. Yes, we will have to do integrals for this. And you need to memorize this formula. Do whatever you have to do. Put a flashcard under your pillow at night for the next 3 weeks. I don't care. Whatever it takes. There is a minus sign here. And then it is a fraction. On top, we take y2 of x times f of x. And on the bottom, we put w. Do you remember what w stands for? A little bit earlier this chapter, we talked about it last week. Say it again. The Wronskian. Yes, this is the Wronskian. This is the w. This is the Wronskian of y1 and y2. That's right. So we have to do this integral to get u1. And we also need a formula for u2 of x. This one is also an integral. This one does not have a minus sign though. But what it is again a fraction, y1 of x times f of x over w, again, the Wronskian of y1 and y2 dx. Okay, I'm gonna put boxes here. So I've given you a few things here we need to memorize. We need to learn, I certainly don't think any of you, once I show you the derivation, you're not gonna wanna do the derivation. But essentially, these are the equations. Do take note that there is a minus sign on the U1 formula, but not on the U2 formula. Also take note that the way I like to remember this is that the f of x is on the numerator of everything. The Wronskian is in the denominator of both of them. And the subscripts are flip-flopped. So for the U1, it involves y2. And for the U2, it involves y1. Okay, I'm going to come back in a minute and talk where these equations are coming from. But I would like to finish the example we were working first. And then I'll come back to that. So back to our example that we had up here a minute ago. Now, in our example, the y1 was e to the 6x, and the y2 was x e to the 6x, right? In step 1, we came up with these two solutions, and those would be the y1 and the y2. Okay, so I'd just like to practice how we would implement these formulas here. The first thing I usually like to do before I actually set up the integrals is I like to work out the Wronskian first. So let's just remember how that works, the W here. So this goes back to last week. I didn't recap it too much today, but it's this determinant, if you remember. We build up this matrix, and if you remember how the determinant gets set up, we put our functions on the top row of the matrix. So the y1 and the y2, they just go up there in the first row, e to the 6x and x e to the 6x. And then we start taking derivatives down the matrix, if you remember, until it becomes a square matrix. In this case, it's going to only be a 2 by 2. So it'll be a 6 e to the 6x. And underneath the second term, I actually have to do the product rule. So the first term times the derivative of the second, which is 6x e to the 6x, plus the second term times the derivative of the first, which is just e to the 6x. So there is our determinant. And it's a 2x2, so for this 2x2. So guys, you can already see why I don't want to make you do this for any of those three. We would have a 3x3 Wronskian to begin with. This is already a mess, right? So for a 2x2, it's not too bad. I'm gonna use the little 2x2 formula, AD minus BC, so that would be e to the 6x times 6x e to the 6x plus e to the 6x. And then minus the top right corner is x e to the 6x, and the bottom left corner is 6e to the 6x. So we're working out this Wronskian here. That should be correct if I haven't miscopied anything. If you look at the underlining I'm doing here, I'm gonna try to skip a step here. If I multiply these two underlined parts together, do you realize you're getting exactly what's being subtracted over there? What do you have? E to the 6x and a 6x and another e to the 6x. What is subtracting here? An x, a 6, and 2e to the 6x's. It's exactly the same. These underlined parts cancel. The only thing that survives this calculation from the algebra perspective is the e to the 6x here times this e to the 6x. What is e to the 6x times e to the 6x? E to the 12x, exactly. So that's just e to the 12x, like so. And there you have the Wronskian. Okay? I like to calculate that first before I go into the U1 and the U2 business. But now I'm going to do that. Let's work out U1. U1 is negative of the integral of y2. Here's y2 right here. X e to the 6x. So x e to the 6x. And then also on top we have capital F. And I think it's capital F's right here. This is the capital F of x. So that'll be e to the 6x on top, and then on the bottom, 1 plus x squared. And the bottom also has to have the w on it. The Wronskian goes downstairs. In this case, that's e to the 12x downstairs. So here's my formula for U1. And what happens is the e to the 6x with the e to the 6x on top actually cancels the Wronskian on the bottom. So that's going to make this come out a little bit nicer. So this just becomes negative the integral of x over 1 plus x squared dx. That can be done. It's been a while since we've done a lot of hard integration. This one's just a u substitution. If I let the denominator be equal to u, then the du of that would be 2x dx. I don't have a 2 in the expression right now, but I can put one on top as long as I divide by it out in front. So I'm going to make this into a negative 1/2 of the integral of du over u, basically. So this becomes the ln. We all know the integral of the antiderivative of 1 over u du is the ln of u. In this case, it's supposed to be the absolute value of u, but 1 plus x squared is already positive, so I won't worry about that here. The other thing I'm not going to worry about right here, guys, is adding a plus c. We are only looking for one particular solution in step 2 of this 3-step process. I don't need to find like the general form of U1. I just need to pick one that will work. So I can choose that constant to be 0 and just kind of not think about it. So we'll just leave that off, and that's your U1. Okay? Let's do U2 as well. I'll just do it right here below in the next line. Again, I'm using the formulas. I've just handed you these formulas, right, without proof so far. That's coming. But for the time being, the formula for U2 is the integral of y1 times f. So here's y1, here's f, right? Let's write that down. That's the numerator. We have e to the 6x. And then we have, for f, we have e to the 6x over 1 plus x squared. And then in the denominator, we again have to put the Wronskian, which we already worked out. It was e to the 12x dx. And again, the exponentials on top actually cancel with the Wronskian that's on the bottom. And so what do we have this time? Notice there's no minus sign on this one, but what we have here is 1 over 1 plus x squared. 1 over 1 plus x squared. Anybody remember what that antiderivative would be? Yeah, it involves the arctangent. Actually, yeah, this is just the arctangent of x. And again, there would normally be a plus c on that. If you're doing a legitimate antiderivative, but we don't need the plus c. We're just looking for one antiderivative that works. And so we can use this one. If you decide to add 17 to that, it's still right. It's just it would be a different antiderivative. Okay, so I've worked out u1 and u2. So putting this together then, I can write down the particular solution using the variation of parameters method. So y sub p of x, let's try to squeeze it in right here if I can. It's u1 times y1 plus u2 times y2. So u1 is right here, negative 1/2 of the ln of 1 plus x squared times y1, which we had recorded over there, it was e to the 6x, plus u2 is the arctangent of x, times y2, which was x e to the 6x. So let's put a box around that as well. At this point, our complementary function seems to be long gone, but that's okay. This is the particular solution. So step 3, of course, I'm going to take the easy way out, guys. Step 3 here, y of x equals, you guys know it, y sub c of x plus y sub p of x. And again, since we've already calculated what the complementary function and particular solution are, this is just a matter of plugging in the pieces. So what we've discussed here is an alternative method for step 2. If we don't know how to annihilate capital F, then this alternative method involves taking your complementary function, replacing C1 and C2 with U1 and U2 to get the form of a trial solution that turns out it will work as long as U1 and U2 are calculated with these equations here. That's right. You follow the procedure here? Seems okay. We do have to do some integration. Sorry, that's just the way this works out. So what I can show you, I actually don't want to dwell too long on the justification of those formulas. So in Canvas, again, I've still got the screen up over here. I'm going to go out of this table of integrals and annihilators for a minute, maybe. And go back to the special handouts folder. We're really giving this thing a workout today. So we showed you the engineering applications, then we showed you the table of annihilators. There is another handout down here, it's the one near the bottom, that says variation of parameters on it. It's a little hard to read, let me open it up. What this handout is the derivation of those formulas. And I decided a long time ago that I wasn't really going to require my students to be able to do this derivation. It's actually kind of long, it's not that short. So if you don't feel like taking notes here on this, that's fine because I've got it typed up for you. And this is kind of just for free. Just as a pure mathematician, I don't like to just hand you a formula with no reason at all, which is basically what I've done so far. So what I like to do is provide you with the justification. I know not everybody is as excited about the derivation parts as I am. This is actually an interesting one. You have your, right here at the top, this triple starred equation is your second order. Remember, I'm only going to do this for n equals 2. this is my second order differential equation, y double prime plus something times y prime plus something times y equals f of x, and I wanna solve it, right? And so the first part is to write down the complementary function. So you can see that here, c1 times y1 plus c2 times y2. It's literally what I wrote right here. Same thing again. And then we get into step 2, which is where again, we take this trial solution. You can see it right here on this line. I don't know how to highlight very well. This line right here, maybe. Yeah, that line right there. There it is, guys. You can see it in all its glory. Y sub p is equal to u1 times y1 plus u2 times y2. And what we're gonna do is we are going to take two derivatives of that and plug them back into the original differential equation and just let the dust settle and see what falls out of it, right? And so that's actually what the rest of this handout is. So I kind of abbreviated it here. Y sub p equals u1 y1 plus u2 y2. I took a derivative of it. So that's the derivative by using the product rule. So this equation down here at the bottom, the derivative here requires the product rule. So u1 times y1 prime plus u1 prime times y1 plus u2 times y2 prime plus u2 prime times y2. That's just the product rule. Now, if I take the second derivative, the 4 terms that you see on the bottom of that handout are going to turn into 8 terms because each of them has a product rule with it. And somebody decided that that just gets too messy. It's just too hard to make it work. And so what they did, again, I won't dwell too long on this, is they made an assumption, which is what I wrote as equation A here. They made a simplifying assumption and they said, let's just hope and pray that we can find u1 and u2 so that this equation here, which is u1 prime y1 plus u2 prime y2, such that that equation happens to be 0. This equation, by the way, is 2 of the 4 terms that were on the bottom of the previous slide. So I don't know if I can get these both up here at once. Kind of, sort of. Can you see that? Yeah. Do you see that the second and fourth terms here are actually these 2 terms? And we're going to make this assumption. Now, by making this assumption, we might be screwing ourselves over right now. We might be setting ourselves up to not be able to make this work. But it turns out it will. Somebody's figured this out ahead of time, that it will work. And by making that assumption, our first derivative of y sub p, instead of 4 terms, this assumption allows me to get rid of 2 of those 4 terms and leave me only with 2 terms. For the first derivative of y sub p, I can take the derivative of that, again, using the product rule. So the second derivative does have, instead of 8 terms, only 4 terms. And, oh my goodness, then we plug, like we usually do, we plug the various derivatives into the differential equation. And I had to small size the font on my document to get it to not spill off the page. We plug all of that in, guys, and it turns out that that equation, I won't show you the details, but it turns into an equation here, u1 prime y1 prime plus u2 prime y2 prime equals capital F. That's what it turns in. That's what it boils down to. That's how the dust settles when you substitute in these different derivatives of y sub p into the differential equation. That's what it's going to become. And it turns out that that equation, u1 prime y1 prime plus u2 prime y2 prime equals F, together with the one that we assumed at the top of the page, yeah, I have to kind of scroll this back up. See this equation A right here, maybe that one, and B right here, they can be put into a matrix. What could be better? What could be better in this class than to put them into a matrix equation? And the matrix is this one right here, y1, y2, and then y1 prime, y2 prime, which is looking just like how my Wronskian matrix is made, right? How do we make the Wronskian matrix? Well, yeah, we just lay out our functions on the first row, and we lay out the derivatives on the second row. And guys, you can solve this system. The rest of it's just linear algebra. You can solve this system for the u1 prime, u2 prime by taking the inverse of the Wronskian matrix. It's a 2 by 2. Do you guys remember the inverse of a 2 by 2 for this class? A, B, C, D, inverse. Oh gosh, let's see, it's 1 over AD minus BC. That's gonna be the Wronskian, by the way. That's gonna be Y1, Y2 prime minus Y1 prime, Y2. And then the entries of the matrix, remember you swap the diagonal entries. We're gonna need to know this for our final exam in just a few weeks. And then the other entries pick up minus signs. That's exactly what I'm doing right here. That's why there's some minus signs showing up in that matrix on the right-hand side. And if you then solve for U1 and U2 by integrating the equations that come out of this calculation, you get the U1 and the U2 formulas that are over here. I used to spend like 45 minutes going through this derivation. I don't like to do that anymore, but I at least wanted to give you a short Reader's Digest version of it. And if you are more interested in really deeply understanding what all of these 3-page handout is about, you certainly can come talk to me about it. And I'll go through it more slowly with you, but I just wanted to at least flash it up here to have some idea kind of what this whole thing is about. Okay. Any questions? Joe?
This method would be for the upcoming and the final? Or just-
Oh, we're gonna need to, anything we're learning is always for the final. I'm like that professor who comes in and says, the whole semester, all we're doing is reviewing for the final. Yeah, we'll need to know it from here on out, definitely. So these problems will not be on the homework for this Thursday, this method. The homework for this Thursday is just the annihilator method only. The variation of parameters method will be on the subsequent assignment, which is going to be due next week, I think on Tuesday of next week, along with some stuff from the first part of chapter 9. So, but if you want to get a little bit of a head start, because Thursday's homework shouldn't be too bad, feel free to do that. I'm 4 minutes early. Would you guys go complain to the administration that your tuition dollars have been not put to full good use? If I decided to stop talking 4 minutes early today, I make up for all the times I probably keep you over.
Not at all.
Not at all. All right, we're gonna quit a little early. I don't want to start a new chapter with 4 minutes to go. We'll just go. Thanks for being here, guys. I will look forward to seeing you next time. It's on the syllabus. It's on May 6th. Yeah.
I thought I was worried you change it, that's why. Thank you.
Okay.